3D structural reasoning is an interesting and challenging problem in computer science. It involves giving machines the ability to interpret and reason about the properties and components of 3D structures. 3D structural reasoning encompasses various sub-areas in technology. However, our research specifically focuses on the area of enabling a model to comprehend how components of a structure fit together. Our world is a complex assembly of objects, which themselves are a combination of smaller parts. Cars have wheels and doors, and houses need walls and a roof. Our ability to understand how these components fit together is a key element of what enables us to interact with and shape the world around us. Therefore, providing machines with this skill would naturally lead to a vast array of applications. For example, an AI model capable of understanding the composition of a house could help speed up home design and bring additional creativity. Despite the potential, progress in this area has been hampered by two main challenges. Firstly, the construction of valid structures must adhere to a vast set of complex constraints, many of which are specific to the object. Secondly, the sheer number of potential part arrangements for most structures is immense, yet only a small fraction of these are viable. These challenges led us to believe we can advance progress in this area by developing a system which leverages the power of the transformer model to learn the composition of Lego bricks within a Lego assembly. Transformers are the current leading machine learning architecture in text-based tasks. And although a large number of arrangements are still possible for Lego assemblies, they offer a well-defined set of rules thanks to their famous interlocking studs and tubes. To achieve this, our custom model will be trained on LDR files. These are an open-source, text-based file type which acts as a digital blueprint for Lego assemblies. A transformer model requires a tokenizer to convert the input text into a stream of tokens. These tokens are then fed into a transformer to be used for creating the output token stream. This is then decoded by the tokenizer back into normal text. This project was completed alongside my project partner Zach Shinnick. My specific role was to create a custom LDR tokenizer capable of producing learnable token streams. To achieve this, the project was divided into 3 stages, involving initial tokenizer design, experimentation with additional pre-processing steps, and the integration of the best practices to create maximum performance models. The break and make researchers who also experimented with LDR files created multiple LDR datasets. We sourced their 8-brick OMR and 8-brick RAND datasets. The OMR datasets consist of fan-made Lego assemblies sliced into sets of 8, while the much larger RAND dataset contains randomly generated assemblies. The byte-pair encoding algorithm is the leading tokenization strategy. It works by creating a token for every individual character it encounters while training. Then, for the number of merges, the algorithm finds the most frequent adjacent pair of tokens and merges them to create a new token. This provides increased compression, resulting in shorter token streams for more efficient training and inference. Additionally, the model is able to better generalize to unseen text by instead evaluating the smaller known subunits. A pre-tokenization pattern is also used to split up the text before applying the byte-pair encoding algorithm. This prevents the creation of very long tokens, such as a whole sentence. LDR files are a type of code, the majority of which is numerical data. This prompted the decision to use OpenAI's GPT-4 pre-tokenization pattern, as it's considered to be a significant factor in ChatGPT-4's more advanced capabilities for interpreting code and numerical values. An initial tokenizer named M1 was built from scratch in Python using these features. Unfortunately, this tokenizer was unable to be tested due to our model's transformer requiring a tokenizer implemented with the Hugging Face tokenizer library. This led to the creation of M2, a Hugging Face tokenizer with the exact same behavior as M1. Initial experiments with the OMR and RAND datasets demonstrated a large gap in the maximum vocabulary size for the respective datasets. This prompted the decision to create 3 custom tokenizers to inspect how vocabulary size influences performance. To test the tokenizer's ability to create learnable token streams, a transformer with the GPT-2 configuration was trained on each tokenizer and its respective dataset. These models were then evaluated with a series of metrics to see which tokenizer performed the best. 2 additional models were created to provide baseline scores by training on the RAND and OMR datasets with the pre-trained English GPT-2 tokenizer. Since the purpose of the tokenizer is to create learnable token streams, instead of evaluating the models on unseen data, 1,000 files were randomly selected from the OMR8 and RAND8 datasets. After clearing all metadata, each line in an LDR file represents 1 brick. When testing our models, the first 80% of bricks per assembly is passed to the model. Then, a series of metrics are applied to measure the model's accuracy in predicting the remaining 20% of bricks. The scores for all test assemblies are then averaged to determine the model's mean accuracy for each metric. This is the format of an LDR brick line. Each entry is a feature for the corresponding brick. Our metrics use these entries to evaluate the differences between the target bricks and the predicted bricks. In total, there are 7 metrics including position accuracy, orientation accuracy, 2 metrics for color accuracy, 2 metrics for brick shape accuracy, and then a final metric taken from the break and make paper, which calculates a score based on both shape and color accuracy. In stage 1, a pre-processing step was applied to remove all comments and metadata from the assemblies, as well as round all numbers to 2 decimal places. This helped increase compression and prevent the tokenizer from trying to learn irrelevant tokens. We thought we could further increase the tokenizer's capabilities by testing the addition of another 2 pre-processing steps. Brick lines appear within an LDR file based on the order they are inserted into the assembly. Due to the irregular and individual way users place bricks, the model will likely struggle to find a pattern. Sorting the bricks based on their position will introduce a consistent pattern and ensure bricks near each other will also have their brick lines close together. Thus, a step was implemented to sort brick lines based on their vertical coordinate, and in cases of a tie, they're sorted by their horizontal distance to the centermost vertical axis of the assembly. Another idea involved pursuing a more efficient orientation representation. Quaternions are a way to represent orientation in 3D space using only 4 numbers. This is a massive reduction compared to the 9 numbers used in the LDR files, which represent a rotation matrix. Adding a pre- and post-processing step to convert to and from quaternions will massively reduce the number of tokens required per brick. This led to the creation of 4 additional tokenizers and models to evaluate the pre-processing methods. In the final stage, an Apex tokenizer for each dataset was created by combining the most effective approaches uncovered from Stage 1 and Stage 2. Here are the raw results for Stage 1. The maximum vocabulary size after training M2 was 140 for RAND A and 1041 for OMA A. This is likely a result of the greater variation present in the OMA assemblies, which aren't just generated randomly by a computer. For each of the 5 models, there is no outright winner. Some perform better on certain metrics and worse on others. To determine the better of 2 models, a score is given to each, which is created by summing the percentage improvements for each metric the model performs better on. This ensures the models are compared by magnitude of performance increase, instead of naively counting quantity of metrics won. In this first case, the base tokenizer achieved the highest score. This is likely due to the transformer being able to more effectively learn a smaller set of tokens, instead of wasting time on larger infrequent tokens. Both RAND and OMA datasets confirm the prediction that a custom tokenizer will result in better model performance. This is likely a result of the domain-specific tokens as well as the GPT-4 pre-tokenization pattern's more effective partitioning of code and numbers. Here is the raw model performance for the tokenizers and models created in Stage 2. Sorting provided mixed results. The models trained on the RAND data did significantly better with sorting. Conversely, the OMR trained models perform much worse when sorted, particularly on position, which was the metric expected to improve the most. From visually inspecting the data, many of the RAND assemblies have a much smaller range for their brick coordinates, whereas OMR has a much greater variation. This is likely having some effect which could be explored in future research. Quaternion conversion provided a similar result, with the model trained on RAND data performing better with the conversion and the OMR trained model performing much worse. This again may be because of the increased complexity of the OMR assemblies, thus requiring the accuracy of their original rotation matrix. The final Apex models are intended to have the highest performance by utilizing the M2 tokenizer with a vocabulary size of 140 and all the pre-processing steps from Stage 1 and 2. Although the OMR models performed worse with sorting and quaternion conversions, I still trained an Apex OMR model with these steps to see if their combination might improve things. I compared these models to the previous models from Stage 1 and 2 which had the highest performance. Unsurprisingly, OMR Apex model performed significantly worse with the extra pre-processing steps. However, although RAND models perform better individually with each, when combined, the resulting Apex model also performed worse. Future research should explore why combining these 2 steps results in worse performance. The main findings from this research effort are as follows. Using a custom-designed tokenizer with domain-specific training and pre-processing steps will increase a transformer's ability to interpret an object's 3D composition. This is evident from the gradual progression of model performance from the baseline English tokenizers. The exact optimal design of the tokenizer is not only dependent on the training data type, but also the patterns within the dataset. The simpler and larger RAND dataset responded well to the additional pre-processing steps individually, but the more variable OMR models only demonstrated better performance from a custom tokenizer. One promising area of future exploration would be pursuing a new pre-tokenization pattern. The GPT-4 pattern is tailored to handle multimodal data, like English, multiple code languages, and arithmetic. A pattern properly designed for LDR files would likely provide more concise token stream. Looking even further into the future, by finding a way to attach descriptive labels to the data, models will more easily learn properties of structures. This could potentially even lead to a model capable of receiving a prompt that's then used to guide the generation of a Lego assembly.